Hi, I am Deepshikha from Tokyo Institute of Technology, and today I'll be talking about the influence of roof substructure interaction on the seismic response of double-layered long-span domes. This is a brief overview of my presentation. First, I'll talk about the current IASS guidelines on equivalent static loads for domes, discuss the analysis models and the parametric study results, and finally the conclusions. The current IASS Working Group 8 guidelines recommend using equivalent static loads for domes with single-story substructures using so-called amplification factors. These were proposed based on a study of a medium-sized elastic dome with a 60-meter span. The idea is to model the substructure as an STOF model, estimate the peak acceleration, and multiply it with the amplification factor to obtain the peak roof response. These amplification factors depend on the period and the mass ratio of the substructure T1 to the roof's O1 mode, which is the fundamental mode. To validate this methodology for longer spans with longer periods, we conducted parametric studies on longer 100-meter span domes with single-story substructures. We also constructed roof and substructure models with modeling the roof as a rigid mass to understand the individual modal characteristics. We then varied the substructure stiffness and the roof mass and plotted the obtained roof and the substructure periods on the design acceleration spectrum. When the substructure is very flexible, it's far from the roof modes, and so in the combined model, the substructure sway mode dominates, with a mild participation coming from the O1T1 interaction. When the substructure is stiffer, it is in close proximity to the roof's dominant O1 mode, and therefore in the combined model, these modes tend to dominate. When the substructure is even stiffer, the substructure mode becomes closer to the higher roof modes as well, and therefore the participation of the O1T1 slightly decreases because a significant participation then comes from the higher O2T1 mode interaction. We then performed response spectrum analysis and obtained amplification factors by dividing the peak roof response to the T1 mode's substructure response. We found that the amplification factors estimated were in agreement with the proposed amplification factors. So, in conclusions, the roof substructure interactions therefore depend on the proximity of the respective substructure and roof modes, and combinations of the fundamental roof O1 and substructure T1 tend to dominate. The substructure mode tends to be split into multiple combined modes like that O1 plus T1, O1 minus T1, and the I plus T1, and each attract a portion of the participation of the underlying substructure mode. We found that for substructures with a participation of over 80%, the proposed method in the IASS guidebook is applicable even for long span domes with substructures, as it provides a good estimate of the seismic response and is suitable for the preliminary design of such domes. Since I have some time left, let me show you the latest developments. We continued the study for multi-story substructures to understand the effect of the higher T2 mode and its interaction with the roof modes. When we plotted the periods on the acceleration spectrum, we found that the higher T2 mode is now in close proximity with the O1, O2, and even the higher modes. So then we found that in the combined model also, the higher modes tended to be dominated by these T2O2 plus T2O1 interactions. When we estimated the amplification factors using only the T1 mode response, we found that the amplification factors were higher than the proposed T1 mode's amplification factors, which means that the T2 response is dominant in this region. Therefore, we proposed higher mode amplification factors as a function of the period ratio RT2, which is the ratio of the period T2 to O1 mode. We found that the amplification factor, especially vertically, was up to 3 times higher than the substructure peak response. And so, we proposed that in addition to the current methodology of using the T1 mode response and the amplification factors, we also use the T2 mode's response and estimate the peak acceleration from the second mode and use these proposed amplification factors, and finally add the two responses to obtain the peak roof response. Further, when we looked at the peak ridgeline accelerations, we found that in the case of the vertical acceleration, the response from the T1 mode was negligible because of the longer fundamental period and almost no significant amplification, and the response was therefore governed by the T2 mode's interaction with the roof. This also meant that the forces and the moments obtained from the using only the T1 mode significantly underestimated the actual overall response, and using the T2 mode provided a much more conservative estimate. This has been discussed in much more detail in our paper, and interested listeners are encouraged to have a look. I'll be happy to take any questions. Thank you for listening.